Were all the students present during the Q&A session? I'm just not sure. There are some things I might need to repeat if not.
Sorry, wait a second, Please. Yeah, say again.
Were all the students present during the Q&A session or only a subset?
Hopefully all of them. Yeah, the numbers looked reasonable. Yes, so I think all of them were present. Yeah.
Okay, that's very good. Actually, there were very good questions, so that will save me a little bit of additional time. Now we go back. I'll just again remind you what we're trying to do. So I gave you some qualitative arguments for why the scaling dimensions of the low-lying operators of the form phi to the q have to look like that. So these are the scaling dimensions of, okay, let me write it more precisely. This is the scaling dimensions of operators like that in some interacting quartic theory. We expect look like that. We expect take this form in 2 plus 1 dimensions. And the interacting quartic theory that we were discussing is basically in Euclidean signature just that. And of course, it's extremely implausible that you can ever obtain it in perturbation theory, or maybe even proving it is implausible, but we see it very well in the data and it makes a lot of sense. And okay, so what's the next step? That means that we have our favorite picture for the scaling dimensions where there are some low-lying operators and then some zoo of operators. So that's our picture. And we might want to be a little bit more ambitious. So instead of just making a qualitative prediction for this, for how the envelope, for how these ground states behave as a function of Q, instead of making a qualitative prediction like that, we might want to capture a few of the low-lying states. Okay. So we may want to capture a few low-lying states. And so we want to go beyond just naive scaling. We want to really understand the gap. Let's say the gap to the first excited states and such things. And in the cold gases, we kind of did that. We understood a little bit about the excitations of the ground state. We understood the phonons. We understood the vortex solutions. And today we will develop a formalism to do that in a generic, strongly coupled conformal field theory. It's a very general formalism. And I'll be following the following reference for the second part of the lecture today. So the first part of the lecture today, the first part is I'm gonna explain a little bit more how to write an effective field theory for cold gases. That is just warm up, yes? That will be a nice warm up for the effective field theory in generic strongly interacting systems. The second part will be how to write an effective field theory for strongly interacting systems, such as the O2 model. But I mean, as I said, O2 is just an example. It's valid much more generally. It's a very general effective field theory. And for that second part, I'll be following some recent developments by the group of Hellerman. I'll be using some of their notation if you wanna, Orlando, Refert, Watanabe, and there are many other people that contributed to that development before and after, but I'll just stick to some of their notation for the second part. Okay, so we'll start from the first part. Let's go back to where we feel very safe. We have our action for sodium atoms. Um, I'll be schematic with the coefficients now. Forgive me for that. I won't keep the H bars and I's. You can just do it later. I'll just put the I here because otherwise it really looks amateurish. And and okay, that was a good approximation in the Fermi regime where we only have scattering in the S wave. That's a non-relativistic field theory. You see it's non-relativistic because this is first order derivative rather than second order. Okay. And here, I maybe convince you, maybe not, that we have a good understanding of the ground state. It's a saddle point. The ground state in the large, okay, we took the large n limit with the property that NA divided by the volume is fixed. And that is our famous uh, healing length to the power -2. So that is the scaling limit that we took. And the ground state was like that. And then we had phonon states. We had phonon states which took this form. We had phonon states that took this form, and we even had vortices. Okay. The spectrum of the phonon states was that omega, the frequency of the phonons, was given by the speed of sound times the absolute value of the momentum, and the speed of sound was h bar over mc. This is just a quick review of what we did. And here there is a question that is very obvious, and surprisingly, this is kind of newer. So people have not really realized that in the old days when they understood superfluid theory. The question is what? The question is, what is the effective field theory? Clearly, there is an effective field theory because we have relativistic phonons. We expect that there is an effective field theory that captures the phonons. So the effective field theory should capture these low energy excitations, and they should be approximately relativistic because we see that their dispersion is quadratic. So there should better be some effective field theory with with an approximately relativistic dispersion. In addition, we would like our effective field theory to capture vortices. This is maybe a more contentious point, but we will see that it does. That the effective field theory can capture the. You remember that the vortex had some flow lines, and the flow was decaying algebraically, and we want our effective field theory to at least capture the vortex from far away. We want our effective field theory to see this regime where the velocity decays like inverse with the distance from the core of the vortex. So let's try to understand what are the degrees of freedom. So when you have an effective field theory, we have to understand what are the degrees of freedom. And does anybody have an idea? So starting from this microscopic Lagrangian, this is the actual wave function of sodium atoms. Okay. What should we keep in our effective field theory? What should we integrate out? Anybody in the audience has any suggestion? Maybe? Anybody wants to make a suggestion? What should we keep from the full wave function to write an effective field theory? A hint is that we already saw some kind of signs that there is symmetry breaking. So there is symmetry breaking in the system. So what should the effective field theory contain? Any
Should contain
suggestion?
boson.
Right, very correct. So the way you go from the microscopic theory to the effective field theory is that you write an ansatz, very similar to what you did in your classes when you studied about the Higgs mechanism. You write the wave function as a modulus, times a phase. You write the wave function as the modulus times a phase. And the phase is a function of space-time, and we integrate out the modulus. And something really interesting happens when you do that, even in non-relativistic theories, because if you look at this term, you might say, oh, how are we ever going to get a relativistic theory for fluctuations if our starting point is a non-relativistic theory, right? This is maybe a confusion that you uh, can think about. But the interesting thing is the following. What am I doing? The interesting thing is that if you look deeply into that kinetic term, which is first order, what it does is it combines the radial fluctuation with the phase, with the time derivative of the phase. So if you integrate out the radial fluctuation, actually the time derivative of the phase will appear now quadratically. So I'll show you that technically now. I'll show you how that happens technically. So our effective field theory should be some action of the following form, d squared x dt, and maybe some Lagrangian for phi. It should not contain rho. We imagine integrating out rho. And how can we constrain this effective action? This effective action is constrained because it has to be Galilei invariant. It's actually very fitting that we're in GGI, no? It should be Galilei invariant because the original problem had the Schrödinger symmetry. The original problem was just freely floating sodium atoms with short-range interaction. That problem has Galilei symmetry. It doesn't have relativistic symmetry, but it has Galilei symmetry. The Galilei group, if you don't remember, consists of translations and ghosts. Oh, what happened? Somebody turned me on, and I can hear myself twice now.
Sorry, I wanted to switch on a microphone for to hear the room, but yeah, but it didn't work. So yeah, go back.
Yeah, if there is a question, maybe somebody can just take the microphone. Then
Yeah,
it would
I'll do
be.
it, but yeah,
Oh,
that's
I'm
fine.
sorry that you have to do that.
No, no, that's fine. That's fine. No worries.
Your Garmin will thank you later. Thank you so much. Uh, so this effective filter for the Goldstone boson is constrained by Galilei invariance. And it's also constrained by the fact that this should be a symmetry, because that's how particle number symmetry is realized on the phase. Particle number symmetry on the original wave function rotated the wave function by a phase. When we look at the exponential, it just shifts the phase by a constant. Okay, it's just spontaneously broken. That's usual formalism of Goldstone bosons. And you can ask, how do we construct Galilei invariant effective actions for Goldstone bosons? Because it has to be invariant under shifts, it only can contain derivative. And there is this remarkable fact that there is a quantity called x, I'll call it x, which is completely Galilei invariant. So if you write an action that contains a function of that quantity, it's guaranteed to be Galilei invariant. So it looks like phi dot. It looks like phi dot minus grad phi squared divided by 2m. And in fact, you can even add the trapping potential. So if you add a trap, like a quadratic trap or a container, of course, Galilei invariance is broken. Galilei invariance will be broken because if you have a container, you cannot have boost or you cannot have translations. But if you think about the trapping potential as a background field, you can just follow how it transforms under Galilei transformations, and you can understand that you are allowed to add it here without specifying what it is, and it's still Galilei invariant. So it's like Spurian analysis, that the potential breaks Galilei symmetry, but Spurian analysis allows you to understand how to put the trapping potential inside the action so that Spurian analysis works. So there is this special quantity x, and if we write a Lagrangian for phi, which is any function of x, where the Galilei invariance holds. Okay. So let's write the simplest action for this quantity, which is the quadratic theory. You will see that this actually works for our cold gas to first approximation. That's the effective action for the phase of the wave function. So the action is d2x dt, and I'll write x squared, and I'll write 1 by g. I put this prefactor 1 by g because if you try to compare the predictions of the effective field theory with the full second quantized Schrodinger problem, you'll see that all you need to do to first approximation is to normalize the phase by 1 by g. That's like the stiffness. That's like the stiffness of the phase. Uh, you need to put it there so that the energy matches. So it's like an unknown Wilson coefficient that I'm just telling you what it is. Also, the fact that I call this function P is not an accident. It's actually the pressure. It's actually the pressure, and that's the density. Because what is our solution? Our solution was that this is constant, which is equal to mu. That's our solution for the homogeneous superfluid, because you remember that our wave function was just normalization factor times e to the minus mu it. So phi dot is just a constant, which is minus mu. So the ground state of the superfluid is just a constant phi dot, and that's why we roughly can think about this x as density, and we can think about 1 by g times x squared as pressure, because the action is just the pressure. So let me just write it more explicitly. d2x dt. I'm going to throw away the trapping potential just for simplicity. So we have phi dot minus grad phi squared by 2m squared. So this is, I claim, the first approximation for the superfluid effective field theory. And you can write down the equations of motion. You can write down the boost and translations netter charges. It's a very simple effective field theory. And you can even, as I said, the ground state solution is phi dot equals mu, maybe minus mu. Minus I, minus mu, I guess, or plus mu. I don't think it matters. Let me just make it plus mu for simplicity. So that's the ground state. In this formalism, we can easily study the fluctuations, the phonons. Those would be fluctuations like that. So we take the phase, we add some fluctuations, we stick it back into the action, and we get an action for the fluctuations. So let's do it in real time. Let's do it together in real time, hoping that I won't make a mistake. So I'm just gonna expand around this classical solution like that. I'm just gonna stick it in into the action, and we will see what happens to the fluctuations. And that will give us a very nice explanation of why the fluctuations behave like relativistic particles. So let's do it together. I stick mu t plus delta phi into phi dot. That gives me mu plus delta phi dot. If you see a mistake, let me know because I'm doing it in real time. Then I'm sticking it into grad phi squared by 2m, and mu t doesn't contribute, and I just get minus grad delta phi squared by 2m. I have to square it, and I'm just going to keep quadratic terms. So one quadratic term is mu squared. That's just the ground state energy. So we get mu squared, well, we get some constant that I'm not going to keep. Then we get some linear terms, which are total derivatives, which I'm not going to keep. I'm just going to keep the non-trivial quadratic terms. So we get delta phi dot squared. We get delta phi dot squared. And then we get, from the second term, we get a grad delta phi squared. Maybe there is a factor of mu. by 2m, and maybe there is a minus sign here. So this is equal to, now we'll see if I haven't made a mistake, delta phi dot squared. That should be equal to that. So that's just a relativistic, that looks like a relativistic theory for delta phi. That looks like a relativistic theory, where the speed of light is replaced by the speed of sound squared. And you can do a small check using our formulas. I already gave you formulas for mu. Mu is related to the density, which is related to the healing length. So you can just check at home that this works out. Okay? So why did we get a quadratic theory? It's just because we have an action of this form. And when we expand in fluctuations around the leading order solution, which is the superfluid solution, we will find a quadratic theory which looks relativistic. But here, what is the advantage of an effective action? That now we can go to higher orders, and it's not going to be relativistic to higher orders. And also, the action could be more complicated. Who told me that the effective action for the phase is exactly that? Maybe there is x to the 4. Maybe there is something like derivatives of x to the 4, right? You can then start classifying various terms in the effective action. And what we did is just a leading order approximation. So in this, are there any questions about the phonons from the point of view of effective field theory before I move to vortices?
Why are we throwing away the term involving mu and delta phi dot?
It's a total derivative. Right?
Oh,
You're
right.
gonna
Okay.
get,
Okay. Fine.
yes. Any other questions? Okay, now comes
Sorry.
something very interesting.
Sorry,
Yes.
maybe I just missed the point. We consider first in X the V trap, and then we didn't consider anymore. I don't know, maybe I
Yeah.
missed some. Like in capital X, we say in addition to the the derivative term, there is also the potential trap, like on considering.
Yes.
And
Yes.
then we do not consider it anymore. Like maybe I just
Yes.
missed.
No, you didn't miss anything. You could add a trap. I just wanted to obtain the dispersion relation for phonons moving in infinite space, no trap.
No,
I just
okay.
like one remarkable thing that I emphasized on Monday was that this Schrodinger problem looks like it has linear dispersion at low energies, right? At low momentum. And here we see the explanation. There is an effective field theory, which is non-relativistic for the angle of the wave function, just the phase of the wave function. And if you go to leading order in the effective field theory, the fluctuations behave like a relativistic field. So you saw the Klein-Gordon operator appearing out of the blue, even though we started from a non-relativistic action. I just showed you that the fluctuations obey a Klein-Gordon operator. And I just did it without any trap to simplify the discussion.
Okay, thanks.
Now, a very interesting point regarding when you have an effective action for a phase variable, this is a phase variable, right? Conceptually. Therefore, it's identified up to 2 pi. So phi plus 2 pi is the same as phi. This leads to a very interesting conservation law that does not exist in the fundamental theory of sodium atoms. The conservation law, so we have two conservation law. One is obvious. Let me just write the conservation. One conservation law is just particle number symmetry. Okay, so one conservation law is particle number symmetry. That comes from the U1 symmetry of the sodium atoms. There's nothing surprising about it. Essentially, the current, roughly speaking, the current is like that. J equals phi, Ji equals grad phi. This is not precise. This is just to leading order in the effect in the equation of state. When you include more complicated functions p of x, that will get corrected. This is just a leading order approximation. This is just a conservation of probability in quantum mechanics. The fact that the wave function conserves probability. Nothing interesting about that. But since the phase variable is compact, there is another conservation law with two indices. Okay, and it's conserved because of the epsilon tensor. This is a particular conservation law that is non-trivial only because phi has a 2 pi periodicity. Nowadays in the literature, a conservation law like that is called one-form symmetry. Oh my God, what happened? It's called one-form symmetry. It means that there are some configurations, kind of defects, around which the fluid, the angle around which phi goes to phi plus 2 pi. And this gives us an effective field theory understanding of what vortices are. So superfluid vortices, from the point of view of the effective field theory, superfluid vortices from the point of view of effective field theory are charged under J mu nu. So you can see superfluid vortices in the effective field theory just as some defect around which phi goes to phi plus 2 pi, and you can even write down the solution. You can even just write down the solution in effective field theory. Of course, in the full theory, we saw that there is a profile to the vortex effective field with this is the healing length, and this is the function chi. Effective field theory will only capture that part, of course. Effective field theory cannot see the core of the vortex, but effective field theory can see the vorticity and the circulation of the fluid at long distances. It's just so in effective field theory, the vortices are charged under a special symmetry that does not exist in sodium atoms. This one-form symmetry is accidental. It doesn't exist in the full theory. Okay, so this finishes the discussion of the effective field theory of sodium atoms. Of course, if you go into that field more deeply, the main question is how to correct the equation of state. What are the corrections? And what happens if the gas is not dilute? What is the equation of state? What is the effective action for X, etc., etc. But Galilean invariance is still a very important constraint. Are there any questions before I go back to strongly interacting conformal field theory?
Hi, I have a question.
Yes.
Unlike the others today, I'm far away from being an expert in this field. So the first question would be this potential. You said that we can view it.
Could you just take the microphone, please?
I am.
Yeah, okay. Yeah, then I could. Yeah, maybe you can try again. I heard very well during the Q&A session. Yeah. Yeah, it's not coming through. The microphone is not working now.
Okay.
Can you try again,
Hi,
please?
do you hear me now?
Yeah, now it's really good.
Okay. Your microphone is the same.
I don't know.
In the field, then.
I don't know why it's not working. It was working so well during the Q&A session. Let me see.
Oh, wait. Can you hear me talking?
Yeah, I can hear you very well. I don't know why you just.
Then you have to speak up. It's just you have to speak up.
Hi.
Yes.
Do you hear
Hi.
me now? Okay.
Yes. I'll just keep it thumb up as long as I can hear.
Okay, my question is related to the potential of the trap. You mentioned that you argued that we can treat it as a field in order to say that the entire thing we wrote down is Galilean invariant. I'm curious about this. Why is the trap potential special? Can we do this for any potential? What does this exactly mean? That's the first question. And the second question is related to explaining this one-form symmetry as a defect, which means that we are moving to like a topological picture, I guess. Why can we do this? But again, I'm not an expert in this field, so sorry. Yeah.
Well, I'm not an expert in that field either, but both questions are very good. First of all, about the trap potential. In non-relativistic quantum mechanics, let me just show you something. Yeah, I'll use that. I won't go back because it will just be a mess. I'll show you. There is something very interesting about non-relativistic quantum mechanics. I'll erase it later. Let's just write the Schrödinger equation. Right? This is the Schrödinger equation, right? Now, in this Schrödinger equation, the potential appears in an interesting way. So let's move the potential to the left-hand side. We can move the potential to the left-hand side and write the Schrödinger equation like that. And now this you might want to interpret as a covariant derivative. What is this covariant derivative? And A0 is identified with V trap. So in non-relativistic quantum mechanics, you can think about a trap or any potential that you learned in undergraduate as a background gauge field. You can think about it as a background gauge field for particle number, which is conservation of probability. So there is the notion of conservation of probability, of course, in non-relativistic quantum mechanics, and the background gauge field for conservation of probability is a trap or a potential. It's just a magic thing about non-relativistic quantum mechanics that the potential, you can think about it as a background gauge field. So it's like gauging probability, the conservation of probability with a background gauge field. So that's why in the effective field theory, we can still follow exactly how the potential enters because it's a background gauge field for U1 symmetry. That's the answer to the first question about why we know the dependence on the trap potential in the effective field theory. Your second question was what? Remind me, it was about the pressure function. What was the second question?
The
The defect, yeah. Yes, in the full theory of, let's say, non-relativistic particles with short-range repulsion, there is no one-form symmetry, and vortices are dynamical particles. Vortices can be created by steering the system. In fact, if you take a superfluid and you start steering it with a spoon, you'll create the vortices that we discussed. I told you about the rotation of the container already. When you go to the low energy theory, vortices become topological defects, kind of. They're not topological in the strict sense. It's just that there is a one-form symmetry that makes the vortices charged. Sometimes in the modern literature on generalized symmetries, this phenomenon is called transmutation. Is that some symmetries that were zero form in the ultraviolet transmute to one form in the infrared. So it's something like that. We know of many physical systems that in the infrared they have topological features like one form symmetry or something like that, but in the microscopic theory they don't have that. So sometimes people call it transmutation. There is a very nice paper about it by Saif Nashari and Seiberg from just a few months ago. If you want to learn about it, I can just put it. Saif Nashari and Seiberg. They introduced this concept of transmutation, of like trying to understand why some higher symmetries emerge in effective field theory. Okay, does that give some sort of an answer to both questions?
Yes, thank you.
I have a question, I guess, in this vein with the one-form symmetries. So I suppose what I would have in mind, if we consider something like Maxwell theory with matter, if you go below, I suppose, the mass gap of your matter field, you have Wilson lines, they have no endpoints now. So you have like a one-form symmetry that corresponds to, I guess, topological loops running around these loop operators. And I guess here in one dimension lower, we're thinking about maybe topological loops around these point-like vortices. I'm just wondering, as you go, I guess, closer to the UV, how does this picture sort of break down in the sense, in the Maxwell theory, maybe you get matter where these lines now can have endpoints. Is there a nice picture for how this one-form symmetry breaks as we go towards the UV here?
Again, a very, very good question. So in the infrared, what happens when we go to effective field theory? We say that the modulus of the wave function is some approximate constant, maybe with small deviations, right? It's a massive degree of freedom, but the phase of the wave function is a dynamical variable that can fluctuate very wildly. Okay, and then we find that these configurations with vorticity, they are protected at long distances. They're protected by this one-form symmetry. But when we go to the ultraviolet, it becomes possible for the modulus of the wave function to go to zero. That's impossible in effective field theory because we expanded around the non-zero value of the modulus. But it's possible for the modulus to go to zero. So what happens is that there could be, that's what happens in the core of the vortex, that the modulus of the wave function goes to zero. And that's why the vortex becomes endable. And so vortices can appear in pairs, for instance. If you take a superfluid and you shake it, two vortices would appear. That's impossible in effective field theory because in effective field theory, well, in effective field theory, vortices cannot really. In effective field theory, you have to extend it a little bit. It's like you said in Maxwell theory. So in Maxwell theory, the charges are very heavy, and pair creation doesn't make sense. But in the full theory, pair creation can happen because the endpoints are actually finite mass objects. So I would say it's completely analogous. The analogy that you drew with Maxwell theory is a very good one. It's in my view, it's basically the same thing. Is that an answer or not? I don't know.
Thank you. Yes, thank you.
Yeah. So one way to say it mathematically is that in effective field theory, if you create a vortex because it's charged under a one-form symmetry, it cannot really move. Because if it were to move, it would change the expectation value of some topological operators. It cannot move. While in a physical theory of like sodium atoms, vortices can definitely move. And yeah, I would say that's a sort of an answer. That's why the one-form symmetry is not exact. Okay. So our goal now is to repeat the effective field theory exercise so that we can capture a few of those states in strongly interacting systems, including n equals 4. I want to capture those states. Our effective field theory should capture those states and maybe even some vortices. Vortices would be kind of almost in the haystack, okay? So vortices are not quite in the haystack, but they're up there. And I should tell you that they have not been seen numerically yet. So people have seen numerically, including in the paper that came out yesterday, some of these low-lying excitations of the ground state at non-zero Q. but they haven't seen vortices yet. Okay, so we have to write an effective field theory, and we have an analog of X. Okay, now previously I just used locality and some kind of picture that dimensional analysis works to say that the energy density scales like density to the power 3/2, and that led to a generic prediction for the scaling dimensions of the ground states. Today, we're going to make another assumption. That's a new assumption that goes beyond just assuming locality. So previously, we just assumed locality, and we had a long discussion yesterday that just this fact that scaling dimensions go like u to the 3/2 is actually consistent with black holes, it's consistent with Fermi surface, it's consistent with superfluid. There are many effective field theories that will have this property. Today we'll make another assumption. We will assume that the low energy effective field theory, let's say in the O2 model, but the same should be true pretty much in any other model. That's a conjecture. So the assumption is that the low energy effective field theory in the O2 model and conjecturally any other CFT. I don't know how to prove, of course, this conjecture, of course. So we're going to make an assumption that the low energy effective filter in the O2 model and conjecturally any other CFT is described by a phase variable. So we'll try to write down an effective filter for a phase variable, and we'll assume that that's a low energy description of these composite operators, which look like phi to the q. Yes? So we're trying to write down an effective field theory for these very heavy operators. And we're just going to assume that the effective field theory is a field theory of a phase of a phase variable, which is 2 pi periodic. I don't know how to prove that, but we'll just assume that. Are there any questions about this assumption? I'm just going to assume that I can describe the spectrum of interacting conformal field theory by this effective field theory of a phase variable. I don't know how to derive it, nor does anybody else, but it seems to be true. It's consistent with the data. And I'm just going to tell you what it gives, this assumption. So we're going to write an effective action, exactly like we did in cold gases, with one great difference. We have to define this variable x. Now we don't use Galilei symmetry. Our conformal field theories are relativistically invariant. So can somebody suggest what replaces x in a relativistically invariant theory? Or it's a lot of hassle for you to bring the microphone? Or
No, it's not.
It's okay.
It's not. But
what is the analog of x in a relativistic theory for phi? Anybody wants to make a suggestion? It's just like you have to guess something that's nearly obvious. I'll just write it. I don't know how much hassle.
Maybe box phi.
Very good. Yes, very close. It's just that. That's a nice Lorentz invariant object, right? Mu goes from 0, 1, 2. Remember that in the non-relativistic theories, the Galilei invariant object was phi minus grad phi squared. If you take the non-relativistic limit, this goes to that. Okay. So I'm just going to write some action that is a function of d mu phi squared. What is the simplest known action that only depends on grad phi squared? You must have seen it a million times already. You will say, oh, it's just this. But this is wrong. Why is it wrong? This system doesn't have any dimensional parameters. What did we do in the sodium atoms? In the sodium atoms, we wrote x squared 1 by g d2x dt. X has dimensions of 1 by time because it was dot phi. This has dimensions of 1 by distance, because it was the short-range interaction scale. This exactly has dimensions of 1 distance squared. This has distance squared times time, and distance and time in non-relativistic theories is the same as distance squared. So the measure is like distance to the 4, and therefore it works out. So this action is perfectly fine, what we wrote from dimensional analysis. You can check it later. But this doesn't make sense as a dimension from dimensional analysis, because phi is dimensionless. Grad has dimensions of 1 over distance. So it doesn't make sense. Can somebody suggest an action made out of grad phi squared that does make sense? Now this I do want the audience to respond. What should I put here for this to make sense dimensionally?
Sorry, that's me, but you're missing a dt probably, right?
Oh, yes. Now I'm missing also a dx. Can somebody suggest what should I do to obtain something dimensionally correct in a theory with no scale? What should I do? So
X squared?
d mu phi squared squared?
Yes.
Wait, but let's count the dimensions. Here there are 3, and here there are 4, if I'm not mistaken.
Okay.
So maybe you can make a new suggestion.
Three halves then. Okay, yeah.
Wait, you're telling me that it's allowed to consider an action where this is an allowed action?
I don't like it, but
You don't like it. We don't like this action, right? This is actually the correct answer. You might have never seen this action before, but this is the correct effective field theory at strong coupling for these operators in conformal field theory. And my purpose today is to tell you how to make sense of this action. It seems non-local, it seems non-analytic, and of course it's just there may be other terms. There could be other corrections to this action. Let me just write one more. You can see there are many other Lorentz invariant actions you can write. This is just the leading one. I'll just write one more that you can see that so you can see that there is more stuff. Actually, at some point I classified a few of them. Let me just find. I classified the few next terms, and I just wanted to show you there is one more that is kind of cool. So the next term that you can write down, I'll just write one in parentheses. It's the next term that you can write down. It's grad squared of the square root of d phi. By square root of d phi, I'll explain what I mean in a second. Divided by d phi to the power 5 halves. You see some crazy stuff going on. By d phi in this particular parenthesis, what I meant here by d phi, I meant the square root of d phi d phi. So you see, you can write some Lorentz invariant actions which are consistent with dimensional analysis, but they look totally crazy, non-local, non-analytic, and we don't like it. I have one comment which is historically very interesting. I don't know what this comment means, but I've been intrigued by it, so maybe one of you will find out. In a completely different field in astrophysics, people have this problem with the rotation curves of stars in galaxies, and the usual explanation is that dark matter changes the Newtonian potential in a galaxy. That's one of the reasons the dark matter was invented. There is an alternative to dark matter which is called modified Newtonian dynamics. Maybe some of you heard this word before. You can read about it on the internet. And this is the effective field theory of modified Newtonian dynamics. That's exactly what the original papers discussed. So they used this 3 halves action to explain to suggest a modification from Newton's laws. So it appeared before in the literature. That's what I'm trying to say, in a completely different context. It's an alternative.
Sorry, Zohar, can I ask a question myself?
Yes.
Is it much worse than Nambu-Goto?
No, that will be my point, actually. Yeah,
Okay.
this is a very good point. This will be my point. I'll explain why it's okay. First, I wanted to say that this action with 3 halves appeared before in modified Newtonian dynamics. I'm not suggesting that modified Newtonian dynamics is correct. I'm just saying that it appeared before this action. Secondly, why does this make sense? This makes sense because of the following reason. We are not expanding the action around phi equals 0. If you try to quantize this action as a fundamental field theory, you would run into trouble because it's non-local and non-analytic. And it's the same with Nambu-Goto action. We don't expand the Nambu-Goto action around vanishing configurations. That would lead to a terribly non-analytic answer. And indeed, the strings have to live in 26 dimensions because of that. You can quantize the Nambu-Goto action around the origin only in 26 dimensions. Similarly here, we're not trying to expand around the vanishing field phi equals to 0. Rather, we're expanding around a configuration with some non-zero amount of particles, which is QT. We're expanding around this configuration because we have to tell the effective field theory that what we're interested in are operators with charge Q. Okay, this is some Q. And we're putting it in the effective field theory by never expanding around the origin. Like in Nambu-Goto, where we expand around Minkowski space, a long string in Minkowski space. Here we're expanding around the superfluid with Q particles. Okay. So that's why this action is allowed. We're never going to try to quantize it as a fundamental theory. We're only going to quantize the small fluctuations around this background. So let's denote these fluctuations by delta phi and work out their quadratic dispersion. That's the same thing that we did with sodium atoms. Let's work out the quadratic dispersion. Are there any questions about this action? Or why is it allowed to consider these crazy looking actions with denominators and all these things? And non-analytic powers.
Right.
Yes?
Okay, can you
just speak louder because it's again stuttering.
that by introducing some auxiliary field, we can make this action prettier? I'm thinking about number of action and the Polyakov action in string.
That's a really good comment. I've never thought about it. I don't have an answer.
Okay, thank you.
Any other questions? Okay. I'm just going to work out the dispersion now because that will tell us about excitations of the strongly coupled states in, let's say, strongly coupled conformal field theory. And maybe I'll make one comment about vortices and we move on. So let me just do this one last calculation of the dispersion. The result is very neat and it has been recently observed, and that's why I'm going to do it. That's why I'm going to do the calculation for you. So you just shove it into the action. You take this ansatz, you shove it into this action with the 3 halves. And by the way, I need to put some constant here, some dimensionless numbers, C. Okay, with this dimensionless number cannot be determined from first principles. It has to be measured or calculated. So anyway, you just shove the quadratic expansion into this action. You go to quadratic order in delta phi, and you get an action for the fluctuations. These are the phonons. It's a small exercise, just expanding to quadratic order a given action. And what you find up to a constant, let me just put up to a constant. I'm not going to keep the overall constant. You find something super similar to what we had in the cold gases, except that in the cold gases, the speed of sound depended on the healing length. It was an unknown parameter that depends on the atoms that you use. Here, the speed of sound is completely fixed. It's a half. So the square is a half, so the speed of sound is that. Okay? So remarkably, here the phonons have move exactly at a velocity, which is 1 by square root of 2 of the speed of light. Phonons in these states move exactly at 1 by square root of 2 of the speed of light. That allows us to write their dispersion relation in infinite volume. We just get 1 by square root of 2, k. But remember that to obtain the spectrum of scaling dimensions, we don't study the theory in infinite volume. We study the theory on the sphere. And therefore, we just have to adopt the dispersion relation to the sphere. On the sphere, we don't have translations, so we don't have a momentum variable, but we have angular momentum. S2 wave functions, or S2 phonons, are classified by their angular momentum, J, which is a representation of SU2. And the dictionary is that K in infinite volume is analogous to the square root of JJ plus 1. JJ plus 1 is just the Casimir of the SU2 spin. You remember that from undergraduate. And therefore, we obtain a formula finally for the scaling dimensions of the phonons. I'm sorry. The scaling dimensions of the phonons are the scaling dimensions of the ground state, which we know goes like q to the power 3/2. That's the same 3/2 as the 3/2 in the action, by the way. Yes? These 3/2 is the same as q to the power 3/2, because to leading order, that is just q. I argued to you that to leading order, the ground state is just phi equals qt, and therefore d mu phi dot squared. Oh, yes, that's a mistake. It was square root of q. I'm sorry. This is a serious mistake. It's square root of q. So the leading order ground state is phi equals square root of q times t, and therefore this is q to the power 3/2. Okay. So we just do this translation, and we get that the scaling dimension of phonon excitations is the scaling dimension of the ground state, which is q to the 3/2, plus the speed of sound. I have to put a square root here. One second. Yeah. And there are corrections from the nonlinear terms. In particular, we see that delta of j equals 2 is delta plus square root of 3. And delta of j equals 1 is delta plus 1. And they were both observed. So what's the main prediction? The main prediction, going back to this qualitative picture, is that yes, we have these ground states here, but we have a prediction for this gap. Let me make it bigger. We have the ground state and we have the gap, and we have the next one. So this is 1, and this is square root of 3. And this is to leading order. Yes, to leading order when Q is a very large number. This is true when Q is very, very large. And as you go to larger and larger Q, this should become more and more precise. This shows you that these effective filters have much more power than just scaling or just dimensional analysis. They actually predict the gaps. And we can hope to see it in experiment or numerics. And even in the idea CFT correspondence, this should be true for the low-lying states large Q. Okay, are there any questions about this superfluid effective theory description of heavy operators in interacting conformal field theory? I'm basically done with this topic. I'm gonna cover now the next topic that I intended to. So are there any questions at all about any of these ideas?
In what regime does the semi-classical approximation begin to break down here?
Excellent question. So what is going on here? You can understand it from this effective filter. You see this effective filter? So this is the leading term, and I neglected this term when I calculated the phonon spectrum. Okay? Do you see the thing that I'm marking now?
Yeah.
Yeah. So I neglected these terms, and I also neglected the million other terms. And I also used the saddle point approximation and expanded to quadratic order. All of these ideas are justified when square root of Q is large.
Okay.
What actually happens when we do numerics is that we can see that this Q to the power 3/2 behavior kicks in, and also the gaps are approximately square root of 3 and 1 already for Q equals 5, I would say, or Q equals even or 6. It seems that it kicks in very, very early, that it's approximately correct, and the strongly coupled theory does have that property already for small q, but mathematically, all these predictions are asymptotic in this limit. Then
Okay.
everything becomes rigorous and unambiguous. The fact that it holds for very small values of q is kind of a miracle of resurgence, maybe. Maybe a miracle of resurgence, yeah.
Okay, I see. Thanks.
Any other questions about this whole business before I move on?
Hi. So I was wondering what maybe I'm confused, but what is the interpretation of the angular momentum J in the CFT? Is it just the spin of the operator?
Yeah, it's just that local operators in conformal field theory, we have an operator like that. That's a primary operator. That's like the ground state. But then you could also have operators like q to the -1, some derivative. Yeah, it still has charge q, but maybe now it has angular momentum 1. So this would be like a phonon in the effective field theory. And maybe the next one would be maybe like that. Yes, this would be some j equals 2 phonon. So these are local operators, and we're trying to measure their scaling exponents. And our prediction from effective field theory is that this will have a higher scaling exponent than the ground state by square root of 3. That's the prediction of effective field theory. It's highly non-trivial, and there is no way to see it in perturbation theory. It's just a prediction of this collective behavior for at large Q.
Yeah, okay, thank you.
Yeah, so we're just discussing the spectrum of primary local operators with possibly with some spin.
Is there maybe a typo in the formula for delta? I think instead of 1/2, it should be 1 over square root of 2.
Yeah, of course, the speed of sound is 1 by square root of 2. Excellent. Good catch.
Okay, thank you.
Let me just check that you get 1 and square root of 3. So when I plug j equals 1, it works out. When I plug j equals 2, it works out. Yes. Thank you. Good catch. By the way, you see it's a parameter-free prediction. We get the prediction for this gap. without any free parameters. Where is I had this picture for the gap. Yeah, we get a prediction for this gap without any free parameters. So as we crank up Q, this should just be correct. I should say that one big open problem in the field is that this effective field theory also predicts some vortices. Maybe the vortices are up here in the haystack. Their energy is quite a bit higher. So I can just write qualitatively, just for the completeness of this lecture, that the delta of a vortex is the delta of the ground state plus maybe something like square root of Q log Q. I think that might be a decent prediction. I have to check the coefficients. That's what I remember. But you see, it's quite a bit higher. It's somewhere in the haystack, but it's protected by this one-form symmetry. I don't think we have seen it yet. We definitely have not seen these operators. Maybe one day we'll see them. And that's still unknown if they really exist in this strongly coupled system. Okay, any final questions? Because the final lecture on Friday will be on a new topic, completely different topic, on which I have prepared slides for you. And I was planning to cover also some spinning operators, but effective field theory of spinning operators, but I asked the organizers to send you my lecture notes on spinning operators so you can just read it there. It's very similar ideas, so you can just learn it on your own. And instead, my plan on Friday is to give a lecture on a completely different topic about entropy. So the Friday lecture will be about entropy. And so for now, if there are more questions about this, I'm happy to answer them. And then on Friday, I'll do something completely different. So maybe if there are any final questions about this whole ideas of semi-classics and large quantum numbers, I can answer it now.
Sorry, the prediction of the gap we have found right now is something that we can predict only with the effective field theory, or is something that we can predict also with the full theory? Because it seems strange that something we can predict with just the effective field theory could not be predicted with the full theory.
The full theory is strongly coupled. We have no idea how to solve it.
Okay.
Let me give you an analogy. We don't know how to solve quantum chromodynamics, right? But if we make a conjecture that the effective field theory is the theory of pions, we can make many predictions. So here I'm doing something similar. I have no idea how to solve these strongly coupled theories like the n equals 4 super Yang-Mills or the O2 model or the Ising model. But I can make predictions assuming that heavy operators are described by an effective field theory. I cannot prove this conjecture. I'm just assuming that heavy operators are governed by semi-classical techniques. And then I can get a ton of predictions that I can go on and check on the computer or an experiment. But I don't know how to prove any of that because I don't know how to prove that effective field theory is the correct framework. Is that okay?
Yes, thanks.
Yeah, this whole development is a conjecture, but it seems to be correct.
I was wondering what predictions you can make about the dual theory, given the statements about low-lying states that you made here.
Yeah, I think. Oh, yeah. I should say that. I should explain that. I actually wanted to. I promised yesterday to explain that, and I forgot. Yes, the dual theory. So in the ADS CFT correspondence, let's say the global symmetry is not O2. The global symmetry is not O2. It's actually SO6. But who cares? It's pretty much the same thing. And if you ask in the ADS CFT correspondence, what is the ground state corresponding to operators like that? You basically ask the same question as what I asked today. The ADS CFT correspondence would say that it's an extremal black hole. It's an extremal black hole. Now, an extremal black hole is very different from what I said today. So let's make a comparison. I'll make a table. Today, I assume that these heavy operators are described by superfluid effective field theory. In the ADS-CFT correspondence, they are described. So today we describe the states. Today we assume that the effective field theory that governs these very heavy operators is the theory of a spontaneously broken U1 symmetry, which leads to gaps like we saw 1 and then square root of 3 and so on. So in the ADS-CFT correspondence, we assume that the effective field theory for these heavy operators are extremal black holes. And that leads to interesting predictions for the spectrum. To understand the spectrum that extremal black holes predict, you have to take into account the quantum fluctuations of the Schwarzian. These are the fluctuations in the throat, the ADS type throat in extremal black holes that was uncovered recently. And actually, what you get is a lot of states, very, very dense. So the number of states here is not order 1. We had an order 1 number of states. And in the ADS-CFT correspondence, the number of states is exponential in the entropy. So it's huge. And therefore, the two pictures don't agree with each other. I would say that this is it's fair to say that the large charge limit of the O2 model, which is a strongly interacting conformal field theory, does not lie in the same universality class as the extremal black holes in ADS-CFT. And okay, so what is the issue? How to resolve this conundrum? What is the correct answer? Maybe also in the O2 model, we should use black holes rather than the superfluid effective field theory. So what's the resolution? In my opinion, the resolution is not known, but the following could be the starting point of the resolution. So first of all, both are correct. Both are probably correct. So why am I saying that both are probably correct? The ADS-CFT correspondence has a lot of supporting evidence, to say it mildly. And also this picture that we derived today has a lot of supporting evidence because we see it very clearly in numerics. As I said in the Q&A session, there is a paper just from today simulating it on the computer, and we can see it very clearly. So both are probably correct. And I think what's going on is that the gauge theory the gauge theory or the quantum field theory that appears in the ADS-CFT correspondence is an SUN gauge theory where n goes to infinity. So the gauge theory that appears in the ADS-CFT correspondence has a very large number of quantum fields, n going to infinity. And that means that when the semi-classical limit, on the other hand, we discussed the O2 model, which has just one complex quantum field. So what could be going on is that the question is, how large is the charge Q? How large is the charge Q? Maybe when the charge is of order n squared, you get black holes. But when the charge is much, much bigger than n squared, you get superfluids. Maybe because there is another large parameter in the problem, which is the number of colors in the of the gauge theory. Well, the rank of the gauge group, I should say, not the number of colors. Because there is this additional large parameter, maybe we have several large Q limits. Maybe Q of order n squared is just black hole type states with a small gap. But when you go to ultimately very large Q, you will get something like what I told you about today. That's one scenario. Another scenario is that extremal black holes, so that's one scenario. I don't know if this scenario is the correct one. Another possible conjecture is that maybe extremal black holes just are not a good approximation. Maybe I'm just saying maybe the naive answer of supergravity is wrong. Maybe extremal black holes are just not right. what do I mean by this stupid sounding statement? When we have an extremal black hole, this is just the event horizon, imagine. If you have any quantum field near an extremal black hole in supergravity, this is now in ADS5, in the bulk. It's not this, let's call these fields not phi because I had phi already. Let's call them some quantum field. I don't know, what should I call it? Chi. I already had chi. Okay, I'll just keep calling it phi, hoping no confusion. So it's well known from the work of Steve Gapser that if you have quantum fields moving around charged extremal black holes, they develop some kind of instability to fall into the black hole and then create one big explosion. So there is some kind of explosion. It's a quantum analog of the Penrose process. Penrose talked about the fact that you can extract energy from the ergosphere. Maybe you remember that. That's a classical statement. In quantum mechanics, that means that the ergosphere explodes in some vague sense. It's called superradiance. That's the technical word for this explosion is superradiance. So extremal black holes in ADS-CFT are kind of unstable. If you have some light matter fields, they will just make the black hole explode. And one possible conjecture is that after they explode, they turn into a superfluid. Okay. So I don't know what's actually going on. I think it's an open problem. Either in the ADS-CFT correspondence, we have to take the charge to be even larger to see the superfluids, or extremal black holes which are charged just don't exist. Because in every UV complete model of string theory, they will actually explode because of some low-lying charged matter fields that float around. So maybe every UV complete model of string theory actually has this guy's phi that will just make the black hole explode. So I don't know the answer. That's the short story. The ADS-CFT correspondence does not give a superfluid effective theory. It gives many, many low-lying states near the ground state, exponentially many in the entropy. You can read the literature on JT gravity to see the calculation, especially the work of Luca Iliesio and Turiaci and Gustavo Turiaci. So they wrote a very nice paper showing this density of states, discrete states near extremal black holes. And it's definitely not similar to what I told you today with this superfluid excitations with the phonons. So I don't know what's the resolution. Maybe somebody else knows, but I don't know. I suppose the answer is that extremal black holes either don't exist or you need to take the charge to be much larger to make contact between the two fields. Okay? That was my long-winded way of saying that I don't know. Any other questions about this?
When you were talking about earlier today about the O2 group, you scrapped out the rho because only the phase is being broken and you kept the phase phi only in the action, right?
Yes.
So when you are talking about the ADS side, I see you didn't write the conformal subgroup of the ADS5. Is it in the analogous to the modulus of the complex number for the like the case we discussed today?
You're basically trying to propose a way to solve this contradiction by saying that maybe the effective field theory for ADS has more degrees of freedom than just the phase. Did I understand you correctly?
Yes.
Well, one way of interpreting your comment would be to say, yes, indeed. The recent work on JT gravity showed that the effective field theory for these heavy operators, in addition to the phase, has the Schwarzian mode. Okay, so if you write an effective field theory that also includes the Schwarzian mode, you'll get this dense spectrum. So, but now the question is, why is there no Schwarzian mode in the O2 model? And my answer is that I think the Schwarzian mode is an artifact of the large N limit, or it's an artifact of the fact that we neglected matter fields that make the extremal black holes explode. But I don't know what is the answer.
Okay, thanks.
It's something that bothers many people, and I don't really know the answer, to be honest. It is disturbing that what I'm describing is A, definitely correct, and B, does not agree with the ADS-CFT correspondence. But there are two ways out. One is that when we talk about JT gravity and the Schwarzian mode, we're neglecting the effects of string theory, which lead to many, many new light particles, which could make the extremal black hole super radiant. A. B, that in the ADS-CFT correspondence, we take a large N limit. And in the large N limit, maybe there is more stuff going on in addition to the U1 breaking of particle number symmetry. So maybe there are more degrees of freedom in the effective field theory, and you have to go to very large Q to see the eventual phases that I was talking about. In other words, maybe the large Q limit and the large N limit don't commute, okay? So if you take large N first, you get the ADS-CFT correspondence. If you take large Q first, you get what I said. And it's not clear that the limits commute.
Is the dense spectrum in the case of JT related to SYK in some way? And
Yes.
if it is, so like what's different about SYK that leads to a dense spectrum compared to what we're seeing over here in the case of a CFT?
SYK at low energies has a Schwarzian mode because of a approximately spontaneous broken conformal symmetry. Well, what I was assuming is that the conformal symmetry is actually preserved. That's one of the differences.
Okay, yeah.
Yeah, the hallmark of JT gravity and SYK is that at low energies there is a mode that carries the spontaneous breaking of conformal symmetry. That leads to a very continuous, very dense spectrum that's almost continuous. In what I was talking about, I assumed that the low-lying states in the CFT actually preserve conformal symmetry, and the effective filter is compatible with conformal symmetry. So, and the only mode that I was assuming is this phase mode.
Okay, I see.
Yeah, it's same. Yeah, we'll have to wait for somebody to resolve this paradox because I don't know the resolution.
Yeah, thanks.
I'm not sure there is a paradox. Maybe using the word paradox is too strong. It might be that the limits that just don't commute. It's not a paradox, it's more like a puzzle.
I wanted to ask a question going back to the effective field theory for the O2 model. So I was wondering how much does the EFT story depend on the number of dimensions we have? So I guess in 2 dimensions, you wouldn't have the 3/2 power, it would just be squared. And I guess that theory is very well studied with, I guess, sigma models and stuff. And I was wondering what happens if you go to, say, higher dimensions. Can we do things over there?
If you go to 3+1 dimensions, you're very right about what you say, first of all. So in 4 dimensions, the effective field theory is d phi squared. So it's like box phi. It's something like phi. Yeah, I don't think I can write it in a different way. So let me write it here. So the effective field theory in 4 dimensions is d phi. Again, it looks like a very sick theory to quantize because it has 4 fields. It doesn't even have a quadratic term. But as I said, we're not trying to quantize it as a fundamental theory. We are quantizing it as an effective field theory where we expand around phi equals square root of q times t. That's what we're doing.
Yeah. Another thing I sort of noticed is, in the last lecture we had that in general dimensions, is it the spectrum scale like q to the d plus 1 over d.
Yes.
But here we, I think the power that you need to put into the action is d plus 1 over 2, I guess. But that sort of only agrees when d is 2 or 2.
Yeah, it's just that this power also changes. This power changes.
Okay. Okay, that makes sense.
Yeah, in general, the answer would be, I think what you said, it's going to be d plus 1 by d. It will come from the power of d phi squared in the action, but also the classical saddle point. You have to understand carefully what's the relation between the classical saddle point and the charge
Yes, okay.
by doing the netter procedure.
Yeah, I'm happy with that. Thanks.
Yeah, yeah. So I think the general Q dependence would be 2 by d minus 2 by d. I think 2 by d minus 2 by d plus 1 maybe. Yeah, so you can just work out this power by dimensional analysis and or by just writing the netter charge, and you can put it in and you'll get what you said, which is q d plus 1 by d. Any other question?
So, in the dual theory language, we've been sort of thinking about black holes, which has some electric charge, right?
Yeah.
Plus the Q. If you consider, this might be a simple yes or no question, but if you consider rotating black holes and take the limit where the rotation parameter, the angular momentum, becomes really large, do you see the same kind of spectrum, or do you expect to see a similar spectrum?
Yeah, this is a very prescient question, if I'm pronouncing that word correctly. I asked the organizers to circulate my lecture notes. It's like 50 pages. I don't know if they did. Did they?
No, not yet, but we
Not
will
yet.
today.
Oh, great. So if you look at the last 20 pages, it's exactly what you said. I wrote 20 pages about the subject, but I'm not going to explain it in this school. I think you can just read it there. Instead, I'm going to teach something different on Friday, but it's exactly about what you said. I worked out the effective field theory for large spin. I found the gaps. I found the degeneracies. I compared to data. And on the other hand, of course, ADS-CFT does not agree with me. It's again the same paradox or puzzle. In the ADS-CFT correspondence, you get extremal rotating black holes, which are again unstable to explosions. But you get extremal rotating black holes, and it's very different. They have a very small gap, and it doesn't agree. I should say, though, I should maybe publicize a paper by Shiraz Minwala and collaborators. They made an important step towards resolving this paradox. They started from extremal black holes in ADS-CFT, which are supposed to be unstable to explosions. But they actually showed something very interesting, that when you take very large angular momentum, the black holes start to fragment. And this paper is called the gray galaxies. So the word that they used is gray galaxy. Because they think about these fragments as gray galaxies. So I think it's an indication that maybe the story will make sense eventually. That when you really go to large angular momentum, the black hole just fragments into these little partons, if you want, or little galaxies, and you get the phase that I wrote in my lectures that the organizers will send you, and you'll get eventually the correct spectrum. But you need to go to large angular momentum for that, maybe much bigger than n squared. Okay? Is that an answer?
Yep, thank you.
Yeah, so I think eventually this puzzle will be resolved one way or another, but we have to wait and see. Maybe also the charged black holes have some instability, in addition to the explosion by light fields. I don't know. That would be maybe to fragmentation. I don't know. Yeah. Fragmentation. Yeah, it doesn't sound right. For the
Hi.
rotating black hole, it sounds right that they would want to fragment because there is so much centrifugal force that makes sense that they want to fragment into these gray galaxies. Yeah, for charged black holes, maybe it's less. I don't know. Yep.
Hi. Sorry, I think I don't understand the physics behind the speed of sound that you derived, because we use the fact that we expand near low slowing modes, right? So phonons are slow, and the speed of sound was order one of the speed of light, right? So I don't understand how this works out together.
No, I wouldn't say that the phonons were slow. It was just that these were the lowest energy excitations. They're very soft. I wouldn't say that they're slow. They're just very soft. They have a very small energy. Effective filter is okay with fast modes. Effective filter is not okay with high energy modes. So the phonons are fast. You're right. I mean, they move just very slightly below the speed of sound, the speed of light. But the phonons are quick, but they carry very little energy, and so effective filtering can capture them effectively. Even in the sodium atoms, if you put in the numbers, the speed of sound could be very large numerically. It's okay because effective filtering doesn't care about that. It only cares about these modes being low energy. The effective filter expansion is in like energy essentially, or density, but it's not in the speed. Speed is not a thing. Is that an answer? Sorry.
Yes, thank you.
Yeah. Okay. If there are no more questions, or let me see.
Okay, good.
Okay.
So
I'll see you on Friday. On Friday,
yeah,
it will be a completely different topic about
okay,
entropy.
perfect.
Good.
See you on Friday. Bye.
Okay. Bye bye.